Hello, my name is Mark Shibben, and today I'm going to talk about quantefi. I've been a modeler for over 20 years, mostly in the finance industry, but also in some other industries, such as aerospace. So, let me start by explaining what is Monte Carlo. Monte Carlo is a powerful simulation method, and in the financial industry, it's used to simulate financial metrics, such as prices. So, financial institutions will simulate these changes in prices, and they'll look and see how their assets and liabilities change as a result of those changes in asset prices. It can be very time consuming and very intensive. In some cases it can require enormous computing resources such as grid computing and cloud computing. So what we're going to talk about today is how quantefi has been able to reduce the amount of compute time. And in the example here that I'm going to go through, we have reduced the compute time of this example from about 16 compute hours to less than 30 seconds. So how do we do that? Well, Monte Carlo is simulating price changes, and it's doing that by creating a bunch of random price changes. That is, in essence, noisy data. Machine learning is a way to find patterns in noisy data. So really, the two can actually work together. So the use case we're going to talk about is variable annuity guarantees. Monte Carlo can be applied to a lot of different types of financial instruments. I'm going to talk about one in particular called variable annuity guarantees. Now, a variable annuity is basically a retirement account, like a 401k or an IRA. You can purchase guarantees upon this account, like insurance, that guarantees the value of that account. And there's a lot of different kinds of these guarantees. They can just be a flat number, a flat value, or it can be a changing value. The value of these guarantees can be complicated and difficult to evaluate, but the law regulations requires that insurance companies do in fact come up with a rigorous way to evaluate these using a model, and that's where Monte Carlo comes in. There are a number of different things you need to do when you're going to calculate the value of variable annuity, and there's some research out there beyond Monte Carlo to do this, but they only solve some of the problems. They don't solve all of the problems, and Monte Carlo can solve all the problems, but it's just intensive. So for example, just the valuation of the guarantee, and then as I said before, there are different types of guarantees, sometimes called step-up or roll-up guarantees. There are other things you need to do if you're going to calculate the value of a guarantee for a variable annuity. I'm going to talk a little bit more about lapse and hedging. CTE 70 is a risk measurement. I'll talk a little bit about that. And then just the ability to combine different policies with different types of guarantees, and then also to make sure that you have an interest rate model, that you can actually model interest rates. And that's what a LIBOR market model is. These are other features that the quantefi solution can solve that are difficult, much more difficult and unique. There's no one else in the industry that can solve these features without Monte Carlo. And then this allows new functionality to calculate implied volatility or implied lapse given a price and some other parameters. If you want to work backwards and solve for those parameters, you can't do that today because Monte Carlo is so intensive. So how do we do this? So you can think of Monte Carlo as a way to create noisy data. It's a bunch of simulations using random values to create random price changes. So they're not completely random, they're governed by some parameters, but we think of each of these price changes, you can think of them over time as a path. So in these graphs here, these are examples of simulations, and each of those lines is a simulated change in a price, and it's simulated many times. And that way, for each simulation, you can calculate the effect of an asset. How does that asset change over time? An asset, an asset that maybe an asset or a liability that maybe the insurance company has, such as a variable annuity guarantee. Machine learning is a way to find patterns in noisy data, so these two actually can work together pretty well. Mathematical behavior is the process of representing and modeling human behavior using math. An example of this is in survival analysis. Now, survival analysis comes from the field of biostatistics. It's called survival analysis because it was used to estimate how long they would survive. We're talking about behavior here, so really we're just estimating when a decision will be made. And what is that decision? That decision is when will somebody walk away from their policy, when will they close their account, and thereby forfeit their guarantee. That's called lapse. That's a type of mathematical behavior. So at any time, a policyholder may close his or her account and forfeit the guarantee. This also happens in the mortgage industry. It's not necessarily you're forfeiting a guarantee, but it's an example of mathematical behavior when somebody refinances their loan or defaults. If they default or refinance, both of those together is called prepay because the mortgage prepays. The degree to which a person makes this financial decision may depend on something called moneyness. How valuable is that guarantee? So in the case of lapse, you can imagine that somebody is actually walking away from their guarantee, which had value. So if it's not worth anything, they're more likely to do it. But if it's worth a considerable amount of money, they probably won't do that. And in the case of mortgages, someone is more likely to refinance their mortgage when interest rates are lower than they were, when they can reduce their payment and save money on interest. So the graph on the left here is an example of what I was just talking about. The guarantee is somewhere in between 60 and 67. So on the x-axis, we have the account value, and we have these breakpoints, one at 60 and one at 67. So when the account value is high, people are more likely to lapse because their guarantee is not valuable. And when the account value is low, that means the guarantee will kick in and they're less likely to lapse. So this is just an example of a lapse function. And on the right, we have an example of the actual lapsation. So the blue is an example of a path of an account value. Let's say they have a guarantee at 64.5. And then the gray is the accumulated, because at each month that goes by, you're more and more likely to lapse. And this is sort of the key in survival analysis. So you're likely to lapse in a given month, but then over a period of 2, 3, 4 months, you become more and more likely to lapse. It can increase as you get more in the money, and it can slow down when you're out of the money, but yet it accumulates. It always goes up, and that's what the gray is showing. That is, once it becomes in the money, the total accumulated lapsation has slowed down. And that's what we see here on this graph on the right. Okay, so now I'm going to talk about hedging. So on the right here, I have something called the outer loop. It's a simulation of paths. You've got, say, 1,000 paths there, or 10,000 paths. And I've got one path in particular there in red. And what insurance company does is they hedge the value of the guarantee. The reason that they do that is to try and to manage their risk. So they calculate the value of the hedge at each point in time. But how do they calculate the value of that hedge at each point in time? What they need is they need something called a delta. So they take these deltas. At each point in time, they have a different delta, and that'll tell you how much to hedge. It's called delta hedging. But how do you come up with those deltas? Well, if you have a complex guarantee, you have to run another Monte Carlo. So that's why it's called the inner loop here on the left. So for each point on each path, you have to do a whole other simulation to calculate those deltas. This is how this explodes, and this becomes very intensive. In this demo, in order to calculate accuracy, in order to compare the quantefi solution with the traditional Monte Carlo, I use something called a Black-Scholes delta. Black-Scholes delta is fast and easy to compute, so you don't need 16 hours to compare the accuracy. In practice, this is not possible. Because of lapse, there's no known closed form delta. However, quantefi can compute delta that quickly, the same speed as which Black-Scholes delta is computed. And that's how one improvement, one advancement of quantefi is to completely eliminate the intensity of that inner loop, and thus preventing the explosion of 16 hours of compute time. So in summary, at each point in time, calculate the market conditions for that point in time, and then also calculate the hedge for that point in time, and then the profit or loss. And then that creates a distribution. Now, this graph on the right here, the blue line is the probability of the total profit or loss of the entire hedge program, of hedging over the entire period of time. And the orange line is the cumulative probability. And the cumulative probability is what's used often for a risk metric. So CTE 70, which stands for conditional tail expectation, is a type of risk metric where you look at the 70th percentile. And this is a common risk metric that is used in other types of industries. VAR is a risk metric similar to this, and a lot of other risk metrics are what happens to your liability under certain types of financial conditions and what's happening in the tail, meaning this something like the 70th percentile or higher of the cumulative probability distribution. So now to compare the old method to the new method. On this graph here on the left, on the x-axis, is the number of paths in each simulation, and this is in hundreds. So each group contains 100 simulations, and each simulation contains the number of paths indicated on the x-axis in hundreds. So the first bar on the very left means that there's 1,000 paths in that simulation, and that was run 100 times. And the answer for each one of those simulations is a little bit different, and you can see the variation here. The variation is actually kind of large. And in the case of calculating delta, this is completely unacceptable. So this shows how the variation decreases as you increase the number of paths. So on the very right, we have 30,000 paths, and you can see it's not getting much better. So the point is that you really need kind of around 10,000 paths each simulation. So this gets super intensive. This is how the computational intensity is actually required for Monte Carlo. And the computation time increases linearly with the number of simulations. So at 30,000 paths, it's taking 12 seconds per simulation. And this is all done on one machine, one dedicated machine. So the quantefi solution takes less than half a second and has no variation. So that's the answer that the traditional Monte Carlo solution is getting closer and closer to as you increase the number of paths. And so some of the techniques for solving these problems in calculating the value of a hedging program and the value of variable annuity guarantees come from standard stochastic calculus, standard probability and statistics. Lower discrepancy sequences are, it's a field of research about improving the speed and accuracy of Monte Carlo. Some of the more cutting edge stuff, variable augmentation, which is from machine learning, and basis function, kind of what I talked about before about using machine learning to estimate patterns in noisy data. There's a link to a paper here. As I said, some of the more basic earlier stuff in solving this problem, just the valuation of the variable annuity guarantee is just now starting to get out there into the literature. And then survival analysis, just using some of those techniques in a more sophisticated way. And then some trade secrets. Thank you for watching this demo. I hope you got something out of it. There'll be more updates, hopefully, and on social media, but also, of course, at quantefi.com.